Okay, so I'm going to go ahead. It says right here, start here. So I'm going to start with chapter 8, part 4. Okay, so this should be the final part of chapter 8. And we're talking about redox reactions. So we have oxidation, reduction, reaction that is casually known as redox reaction. And it's called a redox reaction because the read comes from the reduction, then the ox comes from the oxidation. So we have redox reaction. These are reactions in which electrons are transferred from one reactant to the other, and they're called oxidation reduction reaction, also known as redox reactions. Okay, so remember, saying oxidation reduction over and over again is a tongue twister for chemists, especially when they have to say a lot of things. So the easiest way to refer to this reaction type is to call it a redox reaction. We're told here many redox reactions involve the reaction of a chemical or a substance with oxygen. So we're seeing the example of how that plays out, right? The substance can be an element. Our element here is a metal, and it's reacting with, this is supposed to be oxygen. This carbon here is a typo. I can't get rid of it because it's an image. I can't just delete the C. So I'm going to just scribble it off. But you have a metal, element metal, reacting with the oxygen to form a metal oxide. So this is our oxide right here. Okay. And then you also have an example here of a compound. And this is a molecular compound. So molecular compound, molecular. Okay. And the compound is also reacting with oxygen to form two oxides, carbon dioxide and water, right? You have an oxide of carbon and an oxide of hydrogen, which is essentially carbon dioxide and water. And then we have another type of element. This time we have an element that's a nonmetal, also reacting with oxygen to form an oxide. Okay. We get the idea that they use the term substance or a chemical to indicate it can be a metal, it can be a nonmetal, or it can be a molecular compound. All of these will react with oxygen to form oxides, okay? These are examples of redox reactions. Now in 1411, we don't focus on this so much. We will see this example play out more if you take organic chemistry, okay? You see the example there. How do we recognize redox reaction? The first one was given to us right here. A chemical reacting with oxygen tends to be an example of a redox reaction. But this to me is very vague. I like more sure ways. The other ways we can identify redox reactions is, we're told here, you have to see electrons being transferred. So reactions where electrons are transferred from one atom to another are redox reactions. So in the chemical reaction, you have to identify an atom or atoms that are losing electrons. And these are going to be oxidized. And this reaction is referred to as oxidation. So once again, you have an atom, let's call it X. When it loses electrons, depending on how many electrons are lost, becomes positively charged. Let's look at X being an example of an atom that loses one electron. It goes from being neutral, right, to being positive charge because it lost the electron. And this is the lost electron right here. This transformation is called oxidation. And they haven't told you anything yet here, but in oxidation transformation, the species or the atom tends to become more positive than it was before it underwent oxidation. So you can see here, X starts with no charge and it ends up being positive charge. Oxidation, once again, becomes more positive. So the species becomes more positive. Okay. Reduction is the opposite. In reduction, we're told atoms gain electrons are being reduced. The reduction is referred to as, or the reaction is referred to as reduction. In this case, you have the element, whatever it is, I'll start with it being 0, gaining an electron, and then it becomes X minus, okay? So you have loss of electrons. And by the way, when you have electrons as products, this is electron as a product, we're going to judge this reaction as oxidation, okay? So when I got to this part in school, I remember thinking, wow, this definition is so deep because it wasn't just one, there wasn't one criteria we used to identify oxidation reduction. There were so many different criteria, and you kind of had to notice one of the many criteria that will tell you if that reaction is redox or not. It took me a while to get comfortable with this. So once I got comfortable, I decided the method I liked the most, and that was using oxidation numbers. We haven't gotten to it yet. I'm kind of getting ahead of myself, right? But let's go back here. Oxidation is identified by loss of electrons. When you're losing electrons, electrons tend to be products, okay? And then reduction is defined as gaining of electrons. When you're gaining electrons, electrons tend to be reactants. So I'm writing it here as reactants, okay? And in this case, the atom, the species is being reduced, and the reaction is referred to as reduction. So we have an example given to us here. Let me go ahead and, as usual, add a page. That way I have more room to write. Add a page. I'm getting a little bit better at this again since I've been making a lot more videos lately. So let's say we have sodium, right? An element, sodium solid. We got two of those. And this is reacting with chlorine gas. It's a Brinkerhoff, remember that, to form 2 sodium chloride solid, okay? So we are trying to track the element. And by the way, in these problems here, we're usually looking at the reactants to see what is being reduced or oxidized. We tend to look at the reactants more than we do the products. So when in doubt, the question that they're asking about, focus on the reactants, okay? So one of these things we think is getting oxidized, the other one is getting reduced. What is getting oxidized, what's getting reduced? For right now, I'll see this sodium here is an element, right? And chlorine is also an element. It's a molecular element, but it's an element. In the compound, sodium is positive as a cation. Remember, when you have the ionic compound, the positive ion tends to be written first. The negative ion is usually written second, right? So we see sodium here going from being solid to becoming sodium positive in the compound. Sodium went from having no charge to being positive. That means it lost 1 electron, okay? Remember I mentioned before, when you have an electron as a product and the species becoming more positive, this is a sign of oxidation, okay? And then chlorine, Cl2, becomes Cl minus, right? Since we have 2 Cl's, we'll put a 2 over here. And in this case, for Cl to become Cl minus, I feel like I'm writing this all wrong, in the wrong position, not really incorrectly. It has to gain 2 electrons, right? And technically, I mentioned before, these reactions depend on each other, right? They feed into each other. They're codependent. Let me finish the second part out. When you have electrons as reactants, I mentioned to you before, and the species becoming more negative, this is a reduction. In a reduction reaction, you can see here, chlorine takes in or reacts with 2 electrons, but the electrons come from sodium. So for us to really react 2 electrons, sodium has to create 2 electrons. So this reaction ends up being doubled. And you can see how in the end, it actually works out in the overall reaction. So it takes 2 sodiums to produce 2 electrons, and the sodium, of course, becomes sodium ion, cation, positive ion. The 2 electrons are then taken in by chlorine, and chlorine gets reduced. So sodium gets oxidized, producing 2 electrons. Chlorine gets reduced, reacting with 2 electrons, right? So they feed into each other. Okay, moving on. This is not my favorite way to define oxidation reduction, but you want to recognize this, because in 1412, if you happen to take 1412 with me or anywhere else, you're going to have to recognize oxidation by the position of the electrons, and then reduction by the position of the electrons, okay? So we just quickly review. We covered identifying redox reactions by a substance reacting with oxygen. That was the first one. The other one is by identifying electron transfer. The oxidation reaction creates electrons. Reduction reaction uses electron, utilizes electron, right? Now we're looking at a different way. This is my best way, okay? Y'all didn't ask, but you've been told. Why? Because I like telling you guys my journey because I feel like it personalizes the whole experience, right? The best way I like to identify redox reactions is by looking at oxidation state. Now, when I was going to school, it wasn't called a state, it was called a number. And I like calling it that because I feel like this is a more universal term, oxidation number versus oxidation state number. So this is how you will use the oxidation number. So we will identify oxidation reaction when we notice an increase in oxidation number. We will identify reduction reaction when we notice a decrease in oxidation number. Okay. Yeah. You know what? I just remembered something. I have to mention it before I continue because now it's kind of weighing on my mind. I forgot to give you guys the acronym that I learned in school. Leo goes GER. So when I was in school, I learned Leo goes GER. And in my school, we had my mascot. I went to A&M Commerce, and our mascot, not my mascot, but our school mascot was a lion named Leo. So when I heard about Leo goes GER, I was like, oh my goodness, Leo, like our Leo. I know. I want to say I was special. I am special. Yes. So Leo goes GER is an acronym that helps us to remember what is oxidation, what is reduction, right? So we have loss of electrons, oxidation, and then gain of electrons, reduction. Okay. Guys, it's very important that you remember these things. I'm showing you how to remember. Some people just look at me like, what is all that for? You have to remember this stuff. For many of you who are science majors, wherever you're going, you will be expected to recall this. This has to be in your head. You can't be, pulling out your phone and then Googling stuff or asking Siri or Alexa. You want to be the one who knows stuff so that you get hired. Anyway, I'm going to get off my soapbox. So loss of electrons, oxidation, gain of electrons, reduction. Okay. Now back to my favorite way. My favorite way is by tracking oxidation numbers. To track oxidation numbers, I like this more because you're going to be following rules. You learn rules on assigning oxidation numbers. Once you assign oxidation numbers, then you judge, are the numbers increasing? Increasing oxidation numbers means oxidation is happening. And then the opposite of increasing is decreasing. Decreasing oxidation numbers means reduction is happening. So when I was in school, I was actually given this definition. I was like, you know what? I feel like it was kind of love at first sight or here. I don't know what to say about that. But when I heard it, I was like, I love this way. Only I'm going to improve upon it and add my little stamp to it, my little contribution to it. In the place of decreasing, I'm going to call this reduction. So I can say a reduction in oxidation number is reduction. Y'all see what I did right there? Listen, I was in middle school. I was trying to be creative because my recall is really bad. I really struggle with remembering. So my recall is really bad. So I knew that at this point, I'm beginning to recognize myself. Like, yeah. So that was my way to remember. A reduction in oxidation number is reduction, right? So here, the assumption is you have gone through, follow the rules, and then assign these numbers, right? So let me tell you something. I used to start with the reduction first because the reduction is the reduction of oxidation numbers. So you go from here, you see the number going from 0. Then the other thing I want to tell you, remember 0 to, in the number line, you have 0 in the middle, positive numbers on the right, negative number on the left. So when you go from left to right, that is oxidation. From right to left, that is reduction. Does that make sense? When you're getting more positive, the numbers are getting bigger and more positive, that's oxidation. When the numbers are getting more negative, that's reduction. So from here, we're going from 0 to -2, that will be reduction, consistent with that. And then 0 to +2, that will be oxidation. So this is how you will use the oxidation numbers, okay, to identify the oxidation and the reduction in the chemical reaction. And we're assigning these to elements. So it can be elements in the whole compound. I'm going to tell you this bottom line. There are times where oxidation numbers will, I shouldn't say will, may overlap with charges. Okay, but here's where you're being cautioned. But please notice, oxidation numbers are not ionic charges. Ionic charges are actual charges that are measurable by experiment. Like you can do an experiment and measure that calcium has a charge of +2. With the oxidation states, oxidation numbers, we're told here these are imaginary numbers. Now, when they say imaginary numbers, please don't start panicking. Don't call me and be like, "What? Are you teaching us imaginary things?" They're not just made up. We're following rules, right? But they're a means to an end. They're imaginary charges assigned based on a set of rules, and they have one purpose only. They're here to tell us what's being oxidized and what's being reduced. Okay? So let's not get caught up with the means to an end. Okay, now the rules. This is my favorite part right here. The rules of assigning oxidation states. Please, please, please learn these rules. And it says right here, the following rules are in order of priority, meaning start from the beginning all the way to the end. Okay? Okay, I'm already laughing. Let me tell you why I'm laughing, so maybe you can laugh with me or not. Even though they say they're in order of priority, y'all know what I'm going to do, right? Yeah, at some point I'm gonna go to the end. And let me tell you why. Because when I was learning this, the rules seemed very long. Like the list technically really only has 5 rules. Yeah, it just seemed very long. But the more I look at the rules, I'm thinking if I were to write the rules, I don't write rules, I don't write things down. But if I were to write the rules, I really probably only really have 3 rules. Maybe 3 rules, maybe 4 at most, versus having 1, 2, 3A, 3B, 4A, 4B, 5, right? Because I feel like when you count all that, you're technically having 1, 2, 3, 4, 5, 6, 7, right? It seemed like a lot of rules when I was learning this. And my teacher kept pulling out these rules that weren't even written down. And it was a little bit confusing. But so when I go through the rules, I'm going to mix the order up to try to make it as easy as I can, or maybe more straightforward, because there is some connection here. Okay. The first one is pretty much rule number 1. In rule number 1, when you're trying to assign oxidation states, they tell you here to go for the free elements. So go after, like, look at your balanced equation, look at your formula, go after the free element. What exactly is the free elements? Look at the periodic table, those elements, except for the Brinkelhoff. Brinkelhoff has to be Brinkelhoff, right? So our example here is sodium. If you have sodium by itself, say you have magnesium by itself, I don't know, potassium by itself, what else? Aluminum by itself, iron by itself. All of these are random elements by themselves. And because they're random elements by themselves, you will assign them an oxidation state of 0, 0, 0, 0, 0. So why are you assigning them oxidation states of 0? At some point, we'll figure this out, which is part of the rule, that the total oxidation state must equal the total charge. Okay? So while I want you guys to memorize the rules, I also want you to understand the rules, because once again, I feel like it's easier to understand the rules and memorize them after understanding the rules. That's just my thoughts, right? Feel free to process this however you want to process it. Okay. So once again, notice that all of these formulas here have no charge. In general, if you have a formula X and it has a charge, the charge will be written on the top right corner, right here. But if nothing is written there, we assume there is no charge. So I'm just going to give you a random element X. And for this random element X, the oxidation number is going to be 0. Why? Because the charge is 0. It's implied, it's not written. Okay. And if I say, yeah, let's just go with that for right now. So for the Brinkelhoff family, if your element is bromine or iodine or nitrogen or hydrogen or oxygen or fluorine, I didn't go through all of them, Brinkel, because Cl is not here, or Cl. All of these have to be in the molecular state for them to have an oxidation number of 0, because we tend to find these elements as diatomic molecules in nature, right? So they have to be written like this for them to have an oxidation number as 0. If they're not written like this, the oxidation number is going to be something else, not 0. Okay, that's why they put that here. Once again, an element by itself. So we're giving the example here. Let's go back to the example of sodium and chlorine. Let me add a page. In our example of the balance equation, let me try to give you this. Say you have a balance equation of iron reacting with oxygen to form iron 3 oxide, like that, okay? What we're saying here is the oxidation state of iron will be 0 because there's no number here, so the charge is assumed to be 0. So the oxidation number also has to be 0, so that in the end, the total oxidation number equal the charge. And that's actually a rule that will play throughout when we're working on this one here. You see it play out, where it's not technically a rule, but it kind of shows up in all the rules. Let me try to be linear. Oh my goodness. I feel like I'm trying to explain too much and I'm kind of going around in circles. But once again, the goal is total oxidation number must equal total charge. Okay, so hopefully I'm making sense. Okay, so once again, this would be 0. Okay, that is rule number 1. Rule number 2 says, I cannot assign this because this is not part of rule number 1. This is a compound here, right? Rule number 2 says, when you have monatomic ions have an oxidation state equal to their charge. You see this rule showing up now, right? Where oxidation state must equal charge. So here, let's say for the same problem, instead of having elemental iron, we had iron 2, or I guess 3 plus, okay? And then we had oxygen 2 minus, for whatever reason, we had that. And then this formed iron 2 or iron 3 oxide like that. This is a hypothetical. Say we had that. Because this time there is a charge here, and we're trying to get the total oxidation number to match the total charge. For this reactant here, the oxidation number will be plus 3. For this reactant here, the oxidation number will be minus 2. Okay? Because for each chemical species, we want the total oxidation number to match the charge. Hopefully that makes sense. So that takes care of rule number 2. But rule number 2 also introduces the oxidation number of the ions in the compound, which I don't want to deal with that here. I actually want to deal with that in rule number 3. Rule number 3 says the sum of the oxidation states of all atoms in the compound is 0. It sounds a lot more like this rule to me, right? So we're told total oxidation state equal total charge. Okay? So in a compound, for example, sodium chloride. In sodium chloride, the overall charge is 0. How do I know it's 0? Because there's no number on the top right normally, right? So the 0 is implied. So whatever the oxidation states of the components are, when you add them up, the total oxidation states must equal the total charge. So in this case here, sodium chloride must equal 0 charge. That means whenever you go through the rules, you will assign sodium to sodium is actually a sodium ion in the compound, and chlorine is actually chloride ion in the compound. Sodium's oxidation number will be plus 1, and then chlorine's oxidation number will be minus 1. When you add these up, what do you get? 0. So 0 equals 0. So we essentially have proven that the total oxidation states equal the total charge, right? So I hope that makes sense. The rule is kind of repeating itself over and over again. Total oxidation state equal total charge. Okay, what if your whole, so rule number 3B, that was 3A, right? 3B, I actually end up going in order. What if the oxidation, your formula is not does have a charge? Yeah. What if your formula has a charge? Then what? What if the chemical formula has a charge? The sum of the oxidation states of all the atoms in the polyatomic ion equal the charge of the ion. So I feel like it's the same rule over and over again. We're stating that rule over and over again. Let me go ahead and pull this down. I'm going to add a page here. So once again, total oxidation number in the formula equal total charge of the formula. So our example here is nitrate, NO3, okay? So let's see, NO3 minus. This formula here has a total charge of -1. So we're told here in the definition, the sum of the oxidation states of all the atoms in the polyatomic ion equals the charge of the ion, meaning that once we assign the oxidation number of nitrogen and oxygen, and we add them all up, the total oxidation number must equal -1 so that it is equal to the charge that is also -1, okay? So here's where I'm going to jump. I'm going to come back to rule 3b, but I want to jump to rule 4. Rule 4, there's a rule for group 1 metals. That's for 4a. It says here, group 1 metals have an oxidation state of +1 in all their compounds. Okay. We don't have a lot of rules in chemistry where the rule applies to all compounds, right? So when we do get that, we want to jump on that. Okay. So if I were writing the rules, which I am not, I will actually put rule number 4a and b right after rule number 2. Okay. Because when you're looking at 3a and 3b, you want to examine the compound you have first, and you want to ask yourself, does the compound have a group 1 metal? If it does, then you want to assign the oxidation states from left to right. And I'll show you how that plays out. Because the group 1 metal must have an oxidation state of +1. It's non-negotiable. And if it's not a group 1 metal, if you have instead rule 4b playing out where you have a compound with the first element being a group 2 metal, you have to assign it first, and you have to assign an oxidation state of +2. So you assign from left to right, okay? So let me give you guys a random example, then I'll come back to this. Say we have calcium oxide. Calcium is a group 2 metal. Because it's a group 2 metal, we have to apply rule 4b. We assign from left to right. So we ionize the compound and recognize that calcium, we have in the formula, we have 1 calcium, and in the formula we have 1 oxygen, right? I'm just kind of giving you the whole number relationship, right? That there's 1 calcium and then there's 1 oxygen. So these are the ions that represent calcium and oxygen. The whole compound has a charge of 0. It hasn't been stated, but it's implied. This is equal to 0. Okay. Since calcium is from group 2, it has to be assigned an oxidation number of +2. Calcium normally has a charge of +2, right? So calcium gets assigned first. So the idea here is whatever oxidation number calcium is, oxygen has to take the complement, the oxidation number that matches, well, not really, it's not really exactly like, okay, let me say it this way. You have to ask yourself, what oxidation number must oxygen be? So when you take the oxidation number from calcium and add it to oxygen, we get 0. And the simple answer for that is -2. Sometimes I feel like I'm trying to overdress it up, right? Oxygen has to adapt to calcium. Oxygen has to be -2 in order for the total oxidation states to end up being 0. So calcium is +2, therefore oxygen has to be -2. Okay, you're thinking, well, I don't know, I can't say what you're thinking. I'll tell you what I used to think. I was like, wait, we did all this talking, all this work just to assign oxidation numbers that match the charges? Aren't oxidation number charges? No, because we're told in the slides back here, way back here, oxidation states or numbers are not ion charges. And so we, like younger me, is like, okay. And then I see something like this. Li, let me think of Li, negative ion, LiCl. How about that? LiCl. And I'm like, okay, assign oxidation states. Once again, we start from left to right. Why left to right? Lithium is a group 1 metal. So lithium gets the oxidation number of +1. It has to, because that's the rule 4A. That means chlorine has to get the oxidation number of -1. So when we add these up, we get a total of 0. Okay, we get a total of 0. Great. Okay, so once again, younger me is like, wait a minute, you just assign oxidation numbers that happen to match the charges. Are you sure oxidation numbers are not charges? And then future me, well, older me is saying to my younger self, yes, they're not. They overlap a lot, but they're not the same thing. Okay, let me show you the instance where they're not the same thing. If we have Na2O2. So for this one here, I have to add more space. I need some space to illustrate the point. So we have Na2O2. This example is going to show you that oxidation numbers aren't necessarily equal to the charges. Okay. In this formula, we have 2 sodiums attached to 2 oxygens. So I'm going to draw 2 circles to represent my sodiums. And then 2 circles will represent the oxygen. Remember, the total here must equal 0 because the whole compound has no charge, right? We know that each sodium, well, the charges of sodium are +1, and then oxygen will be -2, but let's keep going. Since the metal is a group 1 metal, we start assigning from left to right. Sodium gets the oxidation number. That's going to be +1. According to rule 4A, sodium has to be assigned +1. Each sodium will be assigned +1, right? So the question is, what oxidation number must oxygen take on to ensure that the total oxidation number equals 0? Based on what we have here, it cannot be -2, it has to be -1, right? So this cancels out with that, and we get 0. And here's where we see that oxidation number does not match charge, right? The oxygen has to adapt and be a -1 oxidation number for this formula to work out. Okay, now that I've said all that, let's go back here. So how do we assign oxidation numbers when we don't have a group 1 metal or group 2 metal? What do? We assign from right to left. This is something that I mean, it took me a while to kind of pick that up. We're doing that because the teacher was like, well, and she or he was talking fast. To me, it felt like they're talking fast. And I'm like, how are we getting these things? How do we know? Later on, I realized there was a rhythm to it. We're going from right to left if we don't have the special group as the first element, group 1 metal, group 2 metal. If we have group 1 metal, group 2 metal, we'll go from left to right. Okay. So let's work on this one here from right to left. So we have N, we have 1N, and then we have O3. So I'm going to draw circles to represent this, right? And our target is -1. So our goal is when we add all the species we have, we get -1. Let's see how that plays out. We got 1, 2, 3. We're going to have 3 oxygens, and then we're going to have 1 nitrogen, okay? Okay, we're assigning from left to right. So assign oxygen first. Oxygen will get the oxidation number that equal its charge. So the regular charge for oxygen is usually -2. So each oxygen will get assigned -2, -2, -2, -2. When you total this, you get -6, okay? So the question here is, okay, I have a lot going on. Let me erase this here. The question is, if the oxygen totals -6, what must nitrogen be? The 1 nitrogen we have be, so that when we add all this up, we get -1. This has to be +5, right? So the oxygen here has to be oxidation number -2, each oxygen, right? And the nitrogen takes on the oxidation number of +5. Once again, Nitrogen is normally -3 charge, but the oxidation number here is +5 because that's what it has to adapt to in order for the formula to work. Oxidation number doesn't equal charge, even though I wrote, yeah, it's not. They're not equal to each other. The times where they are, that's when they overlap, okay? Okay, let me go ahead and move on because I feel like I'm getting to the point where I'm getting a little tired. It's been a long day. So let me move on so I can get to the end of this chapter. I feel like the more I keep adding pages, the longer the chapter gets. So what I'm gonna do here, y'all, is I'm gonna break this down and I'll do it formula at a time. Okay, I'm gonna just leave it right here and go one at a time. In this table here, they're just kind of showing you how they figure out oxidation states, and they're showing it to you for the element written here: fluorine, hydrogen, oxygen, group 7A metal, or sorry, non-metal, group 6A non-metal. I'm gonna do it for each element so you can see how this plays out. So we got MgF2. Mg is has a special rule. It's a group 2A metal, so we go from left to right. Then we have one magnesium that has to be +2, and we have 2 fluorines, right? Our overall is 0, so that means each fluorine has to have -1, -1, -1. And so we assign it that way. Each magnesium is +2. Please realize you're assigning oxidation states for the elements in the compound for each individual element, not the group together, right? And then -1, okay? That's what it took. For the next one, we got H2O. No special rule for H, so we go from left to right. The one oxygen gets -2 oxidation number because we're assigning it first. So it gets the oxidation number that equals its charges. And then hydrogen, then we have each hydrogen, that's going to be +1, +1. Okay? Yeah, so each hydrogen will be +1. The oxygen will be -2. Because remember, the total here is -2. The total here is +2. When you add these two, you get 0. That's how we figure it out. Okay? So let me go ahead and erase this. Okay, so I got CO2, 2 oxygens, 1 carbon. No special rule for carbon, so we go from right to left. We're assigning the oxygen first. Each oxygen gets the oxidation state that matches its charge. Oxygen is normally -2, -2 to make -4. Since we have 1 carbon, the carbon has to be +4 so that when we add these up, we get a total of 0. So each carbon is -4, each oxygen is each carbon is +4, each oxygen is -2. Okay. Feel free to rewind this and look at it. I'm trying to go through this real quick. I feel like I can feel myself slowly fading away. Carbon, and then we have 4 chlorines, right? 1, 2, 3, 4. I don't know why I draw circles. The circles are not necessary, but you get the idea, right? We have 4 chlorines. Each chlorine is -1, -1, -1, -1, -1. We assign the chlorines first because we're going from right to left. And then the carbon has to adapt as +4. So when we total this, we get -4 total, +4, and these add up to give us 0. Okay. Next one is oops, I hate this new, I mean, I like it, but I'm just slow to learn. H2S. So we're going from right to left, right? We got -2 for the 1 sulfur, and then we got 2 hydrogens, so each has to be +1, right? So each hydrogen is +1, each sulfur is -2. Okay, -2. And that essentially gives you the oxidation states of the components in that formula. Okay. Our last one is NH3. In NH3, you're assigning once again from right to left. Since you're assigning hydrogen first, each hydrogen is +1, +1, +1, right? Because there's 3 hydrogens. The hydrogen gets the oxidation number that normally matches its regular charge. So the nitrogen has to adapt, so it will be -3. Right? Okay, great. So now we're moving on here. In this rule, in this problem here, let me try to give some room to work it out. Okay, I'm gonna write what we're working on. We're working on Cl2, that was A, and then B is Na positive, then C is Kf, then D is CO2, then E is A, B, C, D, E. SO4 2 minus, then F is K2O2. Is that what it is? Yep. Okay. So according to rule number 1, where we said you find a free element, the oxidation state has to match the overall charge of the compound. So here we have 0 oxidation state. So I'm going to write it. Oxidation number is 0. Second one, the oxidation number or state has to match the charge of the overall compound. Our charge is +1, so oxidation number has to also be +1. Here we have 2 ions in the compound, right? And remember, the first element is a group 1 metal, so potassium has to be +1, forcing potassium has to be +1, forcing fluorine to be -1. So the total can be 0. This will be +1, -1. Okay. Here we have 2 oxygens. Oh, sorry. Before we assign the oxygen first, we're assigning from right to left, right? So the oxygen is -2, -2. 2 oxygens, we have to assign the -2 because we're assigning them first. The normal charge for oxygen is -2, forcing carbon to be +4. Okay. So when we total this, we get -4, +4, and these net 0. Okay. So here we're going from right to left again because sulfur is not a group 1 or group 2 metal. Okay. We have 4 oxygens, each are assigned -2, -2, -2, -2 because we're assigning the oxygens first. They get the oxidation state that matches. They get the oxidation state that matches their charge. So the total here is -8. But our overall charge in the formula is -2. So whatever charge or oxidation number sulfur has to be, we need a number that when we add to -8, we get -2. That makes this +6. So when you take +6, add it to -8, you get -2. So each sulfur is +6, each oxygen is -2. Last one. Since potassium is a special metal, group 1 metal, we have 2 of them. Each potassium has to be assigned first. It's going to be +1, +1. That means the oxygen has to adapt. We have 2 of them. Each will be -1, -1. And we're done with that part. Okay. So we just practice how to assign oxidation states to the components in a chemical formula or to the elements. Okay. Now we're finally going to see how this plays out in a chemical reaction. We're making progress, y'all. Okay. So in the chemical reaction, we have this question here that says, oh, I feel like there's some stuff missing here. Oh, okay. Here we're told, using oxidation states to identify oxidation and reduction. So we're given this formula here. Let me see. This is kind of, I have to remember how to copy the formula. Copy. I'm going to add the page here. We're going to identify what is being oxidized and what's being reduced. I know I keep adding the pages, so I'm making the lesson unnecessarily longer, but I need space to kind of expand on it, right? And explain it further. Okay, there. So we go through here and do this quickly. And here's the thing about this process. Once you learn how to assign the oxidation states, it doesn't really change, even if you see the same formula in a different reaction. we go after the free elements. These are the free elements. Magnesium is oxidation state of 0. My teachers used to write the oxidation state inside a circle, so I'm going to do the same thing here. Oxidation state here is 0, okay? And then here we assign from right to left. We have each oxygen being -2. That means each hydrogen is +1 to make the whole compound 0, right? So I just really need the oxidation state. So I'm going to write here +1 -2. I feel like I don't have enough room. Space. Okay, over here, we assign magnesium first as +2 because magnesium is a group 2 metal, so it has to be +2. And we know from the charges before, that means, yeah, hold on a second. Let me stick with the rules. Since each magnesium is +2 and we have one magnesium, that means each hydroxide, oops, why am I writing hydroxide? Each hydroxide has to be -1, -1. But we're taking the hydroxide and saying the whole hydroxide is -1, right? And then within the hydroxide, we're going to be following the rules for that to assign oxidation numbers. Hydrogen will be +1, and we have 1. The total must be -1. That means each oxygen is -2. So -2 + 1 gives us -1. Okay. So the oxygen here is -2. The hydrogen is +1. Okay. That wasn't so bad. Okay. Now that we have this sorted out, let's go through and itemize and see how each element is changing. Magnesium goes from 0 oxidation state to +2 oxidation state. It's going right? Becoming more positive. So that's going to be oxidation. And then hydrogen is going from +1 to +1. That's no difference here from +1 to 0. Hydrogen goes from +1 to 0. That will be reduction. Okay. So we could say magnesium is undergoing oxidation or is being oxidized. And then hydrogen is undergoing reduction. Okay. And that's what they state over here. Once again, go through and find the oxidation number that's becoming more positive or increasing, and that will be oxidation. And the one that's becoming more negative or decreasing, that will be reduction. Or, reducing. Remember that? That will be reduction. Okay, now we're talking agents here. Oxidation and reduction mostly occur simultaneously. If an atom loses electrons, another atom in the reaction must take the electrons. So we don't have electrons just floating around in the air, having nowhere to go, right? They usually, there's one that's a giver of electrons and the other one is going to be a taker of electrons. So the reactant that reduces an element in another reactant is called a reducing agent. The reducing agent contains the element that's being oxidized. The reaction that oxidizes an element in another reactant is called oxidizing agent. The oxidizing agent contains the element that's being reduced. So here's the thing, so it's not confusing. Find the element that's being oxidized. The one that's being oxidized is also the reducing agent. Okay? Find the element that's being reduced. The element that's being reduced is also the oxidizing agent. So going back here to what I was working on, when I said magnesium was undergoing oxidation, it's the reducing agent. And then here, when I said hydrogen was undergoing reduction, it's the oxidizing agent, according to that example or that definition. Okay, so let's take a moment so we're not just memorizing this stuff. Let's talk about the agent. Let's say you had skills, like mad skills, and you had an agent. What is the agent supposed to do for you? What's their value? How are they adding value to your life, right? And normally I'll ask this in my face-to-face class. And the recent thing I was told was, well, they help you get jobs. I'm like, yeah, they help you do what you already do, what you're already designed to do or destined to do, right? So the element undergoing oxidation doesn't cause oxidation in others. It is undergoing oxidation. But because of it undergoing oxidation, it causes reduction in the other element. Like when it shows up oxidizing, right? The other element responds by reducing. So the magnesium is causing reduction in the other element, therefore facilitating reduction, therefore it's an agent of reduction. If magnesium wasn't there, hydrogen would never ever get reduced because it needs an agent to get reduced. And magnesium is the agent of reduction. Meanwhile, while hydrogen is being reduced, hydrogen is an oxidizing agent. It's an agent of oxidation, causing oxidation in magnesium. They have that yin and yang relationship. Not only are they doing stuff, but they're causing the response in their partner, if that makes sense. I don't want to over explain it any more than I've already done. Okay, so let's go ahead and move on and work on this last set of problems. In this last set of problems, we're told here, oops, wrong part. Let me copy this part here and I'll be ready. Okay. Let me add this to a page and then we'll go from there. Add page, close the page. Okay, let me go back here and see what it says. Oh, this is a question. Determine whether or not each reaction is an oxidation reduction reaction. For each oxidation reduction reaction, as in redox reaction, identify the oxidizing agent and the reducing agent. Okay, we can do this. So somehow I placed this in the wrong place, but that's no problem. We're close to the end, so close. I can make it. Okay. Once again, I like these kind of questions, especially the first and the last one. They're so easy to identify, or they're so easy to assign the oxidation numbers of. Magnesium oxidation number of 0 because it's a free element. Oxygen oxidation number of 0 because it's a free element. In the compound, assign magnesium first is a group 2 metal, so it has to have an oxidation number of +2. Since you have one oxygen, the one oxygen has to be -2 for the whole compound to be 0. So we can see right here, magnesium becomes more positive. So this is undergoing oxidation. I'm going to write here, it's the reducing agent. Okay. That means a different color for the other one here. Oxygen goes from 0 to -2. This is undergoing reduction. I'll say here, oxygen is undergoing reduction. And it's also the oxidizing agent. Okay? Yeah, that's how it goes. And remember, these questions are asking you about what's going on with the reactant, not the product. So really, this should be talking about that oxygen, not this oxygen here. Okay? We're talking about the reactants. Over here, let's see. The zinc is oxidation number 0, and then this iron is 0. Okay? Fe2 plus 2, oxidation number, rule number 2, Zn2 plus 2, oxidation number, right? You can see the changes here. Zinc goes from 0 to +2. And then iron goes from +2 to 0. This is going to be a reduction. So iron 2 is undergoing reduction and is an oxidizing agent. The first one is going to undergo oxidation. Zinc is undergoing oxidation. And then it's reducing agent. And that's how it works. Okay. So we have one more and then we are done with this chapter. So over here, I am going to start with, we don't have any elements. So we're going to start with the compounds. We assign from right, oops, from right. No, why is this one here not working? Give me just a moment. From right to left. Okay. So Br will be -1, oxidation number, H will be +1. And then here from right to left, right? Calcium has to be +2. We saw this before, right? In the hydroxide, oxygen was -2 and hydrogen was +1. And over here, calcium has to be +2, and then each bromine has to be -1, -1. But we only want to report one bromine, so I'm going to write the top one and erase the bottom one. Okay, over here, we're assigning from right to left. We did from left to right here. Oxygen has to be -2. Each hydrogen must be +1, +1. So we're going to only report the one, and that will be the top one. Okay. Okay, let's see. Hydrogen goes from +1 to +1 in that first compound. In the second compound, from +1 to +1. So it's not changing. Bromine goes from -1 to -1. Calcium from +2 to +2. Oxygen -2 to -2. So this is not a redox reaction. So how can I confidently say that? Because we don't have any changes in oxidation states. It's the same. In order to have an oxidation reaction, you have to have an increase or a decrease in oxidation states or oxidation number. We are not observing that here, okay? For that reason, we can confidently say not happening. What else do we have? Oh, we are at the end. So let me see how they worked it out. So yeah, they're telling us the first one is a redox reaction. They're showing us what's oxidation, what's reduction. So everything is worked out here. And then here we're told this is not a redox reaction. So I haven't lost anything. I'm just kind of a little bit slow right now. This last one here, we have been told the redox reaction, and of course, zinc is undergoing oxidation that makes it the reducing agent, and then iron is undergoing reduction that makes it the oxidizing agent. And so we are done with chapter 8. Yes, we are done. Okay, so I'm going to end the video right here.